Welcome everyone to the Air Sea Fluxus from Space webinar series. Today we have Philip Conroy from the Technical University Delft, who's going to talk about preparing for harmony, high resolution wind and surface current retrieval. And I'll let you get started, Philip.
All right, thanks very much. And thank you all for joining. My name's Philip, and I'm just going to say a few words about this upcoming European Space Agency mission, Harmony, and how it relates to the oceanographic community and the work that we're doing to prepare for that. So just a little bit about who I am. So I'm relatively new to this community. I'm actually from Canada originally, from Calgary, which is famously not a coastal city. And I studied electrical engineering, and that's my background. Also for my master's degree, where I focused more a bit on space technology, and that's how I got into SAR. And then I did a PhD doing INSAR about monitoring land surface motion. And in my thesis title, I wrote highly dynamic land surface motion, but my idea of what highly dynamic processes are has changed a lot since switching to oceans. And now I'm doing a postdoc as part of the Harmony Ocean Science team. So just to give you a little overview of what this mission will do, it's from the ocean perspective, it is a bistatic extension of Sentinel-1. So what that means is that there's going to be two passive receiver satellites that are going to be in orbit around Sentinel-1, and they will basically provide us two additional lines of sight. And with those two additional lines of sight, we are able to sort of see a two-dimensional surface on the ocean. So if you're familiar with standard SAR ocean products, you have essentially just one dimension that you see things in right now. So this will be a huge improvement in that sense. And we can also go as opposed to scatterometry, we can go to a much higher resolution. So I'll just talk a little bit essentially about that. I think I highlighted it there. Yeah, there's a couple other things relating to oceans that the mission will provide. And one of those is actually we're going to try and estimate wave spectra. This is a bit complicated and it's still in progress, so that's not what we're going to focus on. And there's also an additional payload on board that's a thermal infrared camera. It's called the TIR, and that will do SST and in addition to that, cloud motion vectors. But I'm going to focus on the radar product. So for now, we don't have any way, there's nothing that currently allows us to model, or I should say, allows us to practice doing ocean retrievals with bistatic data. And so we have to model it ourselves, essentially creating synthetic observations. And this is a bit of a complicated overview, and I'm not really going to go into this, but just to give you the basic idea, which is that we start with sort of coupled models of waves and currents that are driven by a wharf run, and that is essentially our input. And it goes through this big chain, and then at the end, it spits out sort of our radar observable, the backscatter, Doppler shift, and these spectral products. We also apply a noise model that sort of simulates what we expect the system to do, so that we have a sort of, hopefully, a representative idea of what the mission will be giving us. So to do this, our idea is essentially to try and simulate a Cal-Val campaign of the mission so that when we get to the actual mission in a few years' time, we'll have some practice with this already. And so by doing that, we're going to essentially mass produce a bunch of SAR ocean simulations. And with that, we have now a huge amount of data in the Mediterranean, and we're looking to add to other areas like the Gulf Stream as well. But for now, this is what we've gotten started with. And I just want to say thanks to Justino and Jordi from Catmar in Barcelona for providing us this huge amount of data. It's been really helpful. What we have is a year's worth of data with 6 days per month at an hourly time step. So that gives us about 10,000 different simulations. So we can really sort of mass produce these SAR simulations. And here on the side, I just gave sort of an idea of what we see. This is a WaveWatch 3 directional wave spectrum, and that's what we're integrating into our simulation. At the output of the forward model, this is what it looks like. I'll just briefly mention that we can't really simulate anything lower than 4 meters per second. The models break down at that point. And so I've just filtered them out, and that's what those white blobs are. But if you ignore those, you can see some interesting stuff. You can really see the atmospheric imprint on the ocean surface, and that's really being well picked up by our simulator. So we're really happy to see that. And I just love watching these GIFs. They're lots of fun. Perhaps more interesting to look at is the Doppler shift. This tells us, about the relative speed of the ocean surface. So in there, we have wave Doppler and current Doppler. Now, one thing that you might notice right away is that the Harmony observations are much less noisy than the Sentinel-1. And that's because we are actually measuring this Doppler in a different way. And so we expect to get a much cleaner signal. And this is also really good because now we'll have 3 relative velocities in different lines of sight. And that's what allows us to estimate this motion on the 2D surface well. Another thing to really pay attention to, which is interesting, is you can see really the effects of wave current interaction here. I'm not sure if you see my mouse pointer, but if you look sort of in the center of the image here, you can really see sort of stable imprints in the Doppler signal that are caused by the currents. And then you can also see, for instance, the larger structures that move fast being caused by the wind. So this is an overview of how we actually estimate wind and currents from the SAR data. So these are the 4 outputs again that I had mentioned from the forward model. And now for the inversion, we run this back and we try to see how well we can estimate the input wind and currents. So that's our output at level 2. We do this by applying GMFs. So this is a standard scatterometric approach. If you're familiar with scatterometry, this shouldn't be anything particularly new, other than the fact that we have some additional SAR spectral observables that we can use to help constrain the estimation. So how do we produce these GMFs? So again, a bistatic radar GMF doesn't really exist, so we have to simulate it somehow. And what we do is we can run the forward model in a simplified mode over a range of predefined input conditions. So instead of using a real scene that comes from our coupled models, we just set wind speed directions, etc., wave ages, and we apply a simplified alpha-Ely wave spectrum. And then you get a very quick and sort of, mean equilibrium response. And then we can just essentially build a lookup table out of this, and we can plot that. And so what we've done is we've compared this Sentinel-1, so the blue curve, sorry, not the blue curve, the yellow curve. We've compared this with CMOD, which is the sort of the empirical GMF that's based on Sentinel-1, and we get more or less an agreement. And this was done by, there's a lot of model parameters that are essentially tuned to match that. So now that we have this GMF, we can go through and apply this. We basically, by comparing our observables to the GMF, we can then minimize that cost function and get the best fitting wind that comes from that. So this is essentially your standard scatterometry right here. And of course, this has the problem that you have a 180-degree ambiguity in the wind direction, which you can see here. Um, and that's in the magnitude response. And the other problem that we have with this is that wave breaking caused by wave current interaction is not captured by this model. This is a wind model only. We can enhance this by incorporating this max parameter. I don't really want to go into explaining what this is right now, but if you know what it is, that's great. But it gives you an idea of the direction that the waves are going in. And by assuming that the wind and the waves are aligned, which is of course not always true, or it's rarely completely true, but it's an approximation that we can make. It helps remove this 180-degree ambiguity. Another great thing is that this parameter is not really very sensitive to wave breaking. And so any biases by the wave breaking, by including this term in this way, we can help mitigate that. And it, of course, helps remove this 180-degree problem. A final thing we can do is sort of introduce an initial guess. This is sort of standard practice in scatterometry. So in our case, we introduce a very low resolution result, 10 by 10 kilometer. So this gives us a sort of an initial guess. Operationally, I think this could come from weather models. And this can help resolve the 180-degree issues as well. But yeah, it goes wrong sort of along fronts if you want a high resolution result. And that's where these observables should really be given more weight. This is just to give you a sort of an initial value. So this is what our results look like. So these are 1 by 1 kilometer estimations. So in the left-hand column, you see the input wind and current scenes. And then in the middle, you see our estimations. And then on the right-hand side, you have the errors in the wind and currents. So in this example, we have a really great wind estimate. There's very low error. In the current, we have actually also overall is quite good, but you can see there's a couple hot spots where things go wrong. And in this case, I think this is being caused by the fact that there's a misalignment of the wind and wave vectors because this is sort of on the leeward side of these islands. So you can see here we have, despite the fact there's good wind estimate, the waves are not going to necessarily be following the wind in these shielded areas. And so you might have a wave system that's moving a little bit differently. That causes us to estimate the wrong wave Doppler. And then when we correct for that in the overall Doppler term, you're left with a wrong estimate of the current term. Here's another example off the California coast. Here's another example of how the current estimation can go wrong actually as well. So in this case, again, for most of the areas, we get a great estimate, but then there's sort of a hot spot where you can see there's a huge current here and a particularly strong gradient across it. What that does is it leads to a lot of wave breaking. A lot of wave breaking leads to an overestimation in the wind speed, which means we have wind speed error. That leads to an error in the wave Doppler because you've assigned the wrong speed to that. And then ultimately that also filters back down into the current estimation. So there's a couple different things that can go wrong that we're essentially now working on trying to fix. So the message is most of the time it works fine, but then in the most interesting areas that we really want to get great data in, we need to do a bit more to improve this estimation. Here's just a summary, just to show overall these results, we get sort of an unbiased thing, but that's also because we don't model certain noise biases in the system. So this is essentially just what we expect to see. And on the California plot, you can see here, there's these biases, again, caused by that, that large current up in the north part of the scene. Again, just a few words on the wind wave alignment. So right now, we estimate or we assume the wind and the waves are aligned, and that's how we remove this wave Doppler component. And you can see that's not always true. So on the left-hand plot, this is kind of an ugly plot, but what I've done here is I've just taken the peak wave number direction from the WaveWatch 3 spectrum, and I've subtracted it from the wind speed vector. And that shows you a kind of alignment or misalignment between the wind and the waves. And you can see, especially in the low wind scenarios, you can have non-local wave systems that are sort of dominating. And those are the cases where our current estimation will suffer. So that's another way of showing what's going on there. Now, this is what I've been working on lately, which is just crunching through all those simulated data sets that I was talking about. And the idea is to produce a better GMF that's not just based on this alpha Healy spectrum. This will also include non-equilibrium conditions. It will also have a wave current interaction, things like that. Right now, I have about 200 million points in here. And more importantly, this also simulates the mission's Cal-Val phase and will give us an idea of how to deal with its data and what to do with it. So here, for fun, I've just kind of plotted out the scatterometric cone. So you can see in the z-axis, this is the radar backscatter, so the observed power scattered back to the radar versus the wind directions. And you can see we have a huge number of data points. I think to make this thing without killing my computer, I had to filter it down to 25,000 points out of 200 million. But it's just to give you an idea that we have a huge portion covered. That being said, this is also still just based on the Mediterranean, where conditions are going to be different than in the open ocean, for example. And we might have to rerun this exercise, or we will have to rerun this exercise for those other areas as well. Another thing that we're working on is considering the polarimetry of the observables. I'm not sure how familiar this audience is with this, but the polarization of a radar signal just tells you the direction that the electromagnetic wave is fluctuating in. And they're always usually emitted in sort of one direction. And then they reflect back either aligned in that direction or perpendicular to that. And we have, in the sort of standard SAR world, we have sort of vertical and horizontal polarization. Now, because we're observing for these two harmony companions, we're observing from different geometry. This results in a rotation of the polarization vector. Now, this allows us to actually, as a side effect, it actually makes the system act like a compact pole system, which means we can get polarization diversity in our measurements just as a side effect of this geometry. It's not actually optimized for this, so this angle is not very large, which means this is a suboptimal setup for that, but we might be able to take advantage of it. And the way we can take advantage of it is by observing the fact that wave breaking generally creates a non-polarized return, which means that it will be in both polarization channels. And when we do a bit of algebra, we can essentially isolate this and hopefully remove this term from the observation, and thereby mitigate the effects of wave breaking on our wind estimation. Here's sort of an initial result of that. You can see here we've done a decomposition of the Bragg component. This is the sort of standard mechanism by which SAR signals receive SAR sees wind-driven waves. And then here's an estimation of the wave breaking component. And you can see that wave breaking component, that lines up exactly with those errors that we had in the earlier slide that I showed. So if we can get this well estimated, we should be able to drastically improve the quality of this estimation in these hotspots. So that's ongoing work. And yeah, that's about all I have. I just want to say again, to summarize, the Harmony mission will provide us with sub-mesoscale 2D wind and current products. Our baseline retrieval is based on sort of standard scatterometry, and it works pretty well, it works except for when it doesn't work. And those are sort of in the interesting regions where we want to get better observations. So there's still lots for us to do. And we have this tool now, what we call the scientific workbench. And we have a lot of data that we're crunching through, and hopefully we will soon have new things to show as well with that. So just added a note that if you're sitting on a data set that has, coupled wind and wave simulations and you want to get involved, just feel free to contact me. We're always looking for more data to use. So I think that's it. Thanks very much.
Thank you, Philip. And questions? Maybe I'll start with a really basic question. What's the expected revisit time for Harmony to come back to any given location?
So in this wide mode, it's the short answer is 12 days. So the Harmony will orbit around one of the Sentinels, and Sentinel has generally a 12-day revisit, but I'm not sure if that's a global value or if that's just over Europe.
It's a bit it's a bit different. It's a 12-day repeat, which is not the same as a 12-day revisit. So depending on where you are, you have several tracks covering the same area. So the more north you go, the more south you go, the better it becomes. At the equator, then you have a 12-day for ascending and a 12-day for descending. But anyway, but the scales of days.
Thanks. Chidon, you have your hand up.
Yes, I got a little bit distracted during your talk, so I apologize if my question have been addressed during your talk. So if I understand it correctly, one main issue of WaveWatch 3 is that it does not partition the total momentum input from the wind into wave generation and the wave dissipation. I don't know how much this issue will influence the accuracy of your retrieve.
Yeah, that's a very good point. We struggled with this when we were first integrating it into the simulation. So what we have is a sort of 2-scale model where we have what we call the short waves, which is what the radar is actually sensitive to. And then we have the long waves, which is what WaveWatch 3 covers. And then there's a sort of transition that is just estimated between those. It's hard to say how well modeled that transition area is. I don't have a slide. I have a slide for that for a more technical meeting, but I didn't include it in this deck. But we essentially found a way to make it work. It's the long story short. One problem that we really had was that we were massively overestimating the amount of wave breaking in the beginning. And what we had to do was sort of override that with an alpha-Ely estimate with an alpha-Ely spectrum in the wave breaking area just for that term, but using the 2-scale WaveWatch and RIM model for the rest of the simulations. That was sort of a workaround that we were able to use.
Okay, thanks.
Other questions? Can I ask, when you talk about short waves and long waves, what scales are you thinking?
So long wave is this is sort of an arbitrary distinction, but long waves in this case is what's covered by these operational models. And the short waves is like centimeters. So what the C-band Bragg scattering is sensitive to. So that's
Okay.
these little features on the wave.
The capillary or not strictly capillary waves.
Yes, yeah. I'm afraid to use the word capillary. I've gotten corrected when I've said that before.
I use it and I get corrected all the time
Yeah,
too.
yeah.
But I think the distinction that I have a question that follows up on that then, because from an ocean standpoint, we would distinguish between long waves that are swell and short waves that are wind forced surface gravity waves, both longer than the centimeter scale. And you could expect that the swell might be coming from far away and so not necessarily aligned with the local wind, but the shorter waves, which are still long waves by your standard, would be aligned with the wind. And I guess I'm wondering, is there any prospect for being able to separate those two different scales of waves?
Yes, yeah. So that's where the SAR spectrum that I didn't really, I kind of just brushed over that. But we're working now on trying to estimate the wave spectrum, the directional wave spectrum from what we see in the SAR data. So you can also have a SAR spectrum, and we are now looking at what information can we invert from that that tells us about the directionality of these different partitions.
David Wolf, you have your hand up.
Hi, thanks, Philip. I guess I'm just wondering, a slightly less ambitious thing to do with satellite data would rather than be to estimate, would be to, acknowledge that there are operational models around, and to essentially use it as either as a data assimilation tool or a validation tool, as opposed to what is a little bit more ambitious, which is estimating. And sort of I guess one reason you might do that is if you think about the revisit time, which isn't very frequent, soon you're going to have to resort to the operational models quite a lot of the time anyway. So maybe if there's a case for just saying, well, the operational model is the main product, but we can test that operational model and we can maybe assimilate data to that model to improve that model. So I guess that was sort of a suggestion. I don't know if that's something the Harmony team have thought about and rejected, but
no, it's something that actually I think is sort of okay. There's two things I'd like to say. So the first is we actually intend to use sort of the operational models as an initial guess, but those are generally at low resolution. So the whole idea here is we're not going to change the operational models in that way. The idea is how fine scale can we go? So we really want to look at these sub-mesoscale processes in the air-sea interface to really resolve the stress in these fine scales, because that's something that's not really well captured by these models. That being said, in our sort of Bayesian retrieval scheme that is based on what's done in scatterometry now, you start with an initial estimate, and that estimate is indeed the operational model at low resolution. And then we're essentially scaling that up to a high resolution based on our model or based on our observations.
Maybe I can add a bit to this to explain a bit, because this goes a bit in the origin of Harmony. When we propose it, which is I was proposing it, I can explain this a bit more. So if you are building a SAR machine, this is a SAR system, you go for high resolution. If you wanted to do a simulation, you would also want to have the sampling to go with it. You could still assimilate with a poor sampling, but the benefit of that is probably not huge because you are undersampling in time. And Harmony was always seen as a snapshot machine. So we're getting snapshots. We are not sampling in time, but we have a very high sampling in space, except in some regions where if you go to polar regions, then your revisit becomes large enough, high enough that for some of the things we observe, we could assimilate them because we sample properly. But in most of the ocean, these 12 days or 6 days, whatever it is just too long, especially for the scales of the processes that we're looking at. Because we're looking at kilometer scales or 10-kilometer scales, and with a week in between, there's nothing to sample, right? So it's a snapshot machine. That's one part of the answer, and in the end, that we want to use this is to better understand the Shopwell scales in your models, so that you can improve your models. And if somebody wants to simulate, for sure. There's another part of the answer, which is how these missions are set up. So when ESA asks for a proposal for a mission, they actually want your physical products. So if you say, no, we don't care, we are going to assimilate, you don't get selected. So you have to give the promise of a product. And I think we sort of agree, people were proposing the team that it's sort of silly. So at some point you want to have the sensitivity to your physical variables, and then how you're going to use them. It could be a simulation, can be something else. But we cannot do that. We really have to deliver this level 2 products, which are your physical, and you can use them or not. So I would agree that probably in the end there's more value in taking the observables and try to incorporate them to your model directly than to go through the retrieval. But anyway, we have to do this because that's what ESA asks us to do, and it's fun to do anyway.
I suppose a comment about that is, I think, SAR resolution is very high, and it's going to be a very long time before an operational model gets anything like that resolution. But they are inevitably going to be a higher resolution with time, and that's something to anticipate and think about how that changes how we use the satellite data, I think.
Yeah.
Other questions? I guess to follow up on that, one of the excitements I think about Harmony is getting the statistics in a really good sense, so that we can say what the requirements would be for a different observing system, something that had more coverage. And so part of that is really understanding the distribution of wind current interaction statistically. What happens in strong winds, what happens in weak winds, how frequently do those occur? And I guess related to that, my question is, what's the expected performance range for wind speeds? And I ask because the simulations you showed didn't have crazy hurricane force winds or anything.
Yeah, so in this simulation, we're a bit limited by what we can model, which is sort of between 4 to 22 meters per second. So if we go really high or really low, I can't simulate that here. In that range, I can say we're trying to get away from providing RMSEs and things like that, because as you can see, they kind of lie. You have, in a certain area, maybe 0.1 meters per second error, but then you'll have a hotspot where you're off by a full meter per second.
So a non-Gaussian distribution.
Yeah, it just depends on the features in the image. In the sort of easy case, we're really almost just limited by noise, by the speckle. But yeah, like I said, in those error hotspots, we have to do a bit more work to improve the performance.
So what are the prospects for a place like the Southern Ocean, where we have lousy in situ observations and strong winds and high fetch?
So I think because of our right-looking geometry, it favors the North Pole. Paco can correct me if I'm wrong here.
But the Southern Ocean is big.
Yeah.
I think this question is something that you should, as community, if you want the Southern Ocean, we have acquisition mask in the Southern Ocean, part of it, because it's everybody likes it. If that's your area of interest, and if you have good data to compare to, make sure you keep insisting, and then we will add it, because this is the point of also trying to promote the mission to the community, so we get back where you want data.
Yeah, I think that's a good point. And that may be a good message for this group, is I think ESA actually is really looking for input from the community on where to put emphasis. And they're not always like the easiest group to interface with, but I think in the past there's been sort of a disconnect where they produce something and then the community says, "Oh, we're not happy with this," but then they say, "Oh, well, nobody gave us any input." So I think if people are noisy and are insistent, then this should
but
hopefully help.
it's not too bad. If I look
Yeah.
at what's happening with biomass, biomass did not have an ocean mask other than anecdotal, and then we showed that is actually super nice. If I don't know if anybody showed any biomass data in this series. If not, we should.
No, we should get that.
We should get, because it's amazing. So it's really amazing. And they didn't really have an ocean mask for it, but we looked a bit at the data, and then there was a workshop. I was showing there some data, and the people got excited about it, and now they are increasing the critical mass for that. So there is a lot of flexibility in the explorers, because they are science missions. So there is a bit. We are in Harmony a bit limited by the fact that Sentinel-1 needs to transmit what we want to receive, and we do not have control over Sentinel-1. But Sentinel-1 acquires a lot of data in many places, so there is flexibility here. It's not even after the mission gets launched, there is room to play and ask.
Yeah, I think from a community standpoint, understanding the processes in the Southern Ocean, where it is a high wind, high fetch regime, is really important because it's the region of strong ocean uptake of heat and gas. And so really understanding what's happening in those high wind conditions in terms of momentum exchange and the related fluxes is really important. So yeah, Paco and Philip, how does the community weigh in on that? What's the pathway?
And the pathway is what you're doing right now. And so we go around, and then it's good if you don't forget that people are asking for it. It gets more important when there's also people from ESA listening. But yeah, I will share it right now with the people at ESA.
Great.
So that they don't forget. But yeah, we still have a few years to go.
Yeah,
before this really goes.
I think if at some point you want a white paper or something, a one pager, there are ways to get something produced.
Yes, but we do have we do have a document which is still a work in progress, where we went over the different regions of interest with a justification for each of them, and it's very difficult because you have to find that amount of scientists what they want, and they come with their pet regions. But what we should do, and what we will do, is share this, and we can share this with this community, and then you can disagree, and then I will invite you to edit the document. It's a collaborative document in LaTeX and Overleaf, so I could add anybody, and then that could be a way.
Great, thank you.
Yeah.
David, you've got your hand up.
Yeah, I mean, just the obvious thing is the space agencies are based in the Northern Hemisphere. And I think, that is part of the conversation with whether it's ESA or NASA or JAXA or whoever, that when you're talking applications, it's probably a lot easier to convince them that something that's relevant to the Northern Hemisphere. So if it's ESA, if you start getting into coastal sea, OBIS has its advantages in the North Sea, etc. So getting something that's oriented to favour the Southern Hemisphere, in particular the Southern Ocean, yeah, I mean, there's an interest in CO2 exchange, etc. Yeah, absolutely. If you're thinking very globally, yeah, the Southern Ocean is possibly the most interesting place of all. But it is kind of hard to convince space agency in the Northern Hemisphere that they should throw lots of resources at improving the description in the Southern Hemisphere.
Yeah, it's a Southern California surfer question. People want to know where the south swell is, when the south swell is coming, and what drives it. So they're looking at Southern Hemisphere winter storms to drive surf conditions in the Northern Hemisphere summer.
Yeah, but it's good to know. This feedback is already, if it's on our radar, no pun intended, then we bring it up during our interfaces with them as well. So yeah, it can filter through.
That's great. So any other questions before we wrap up? If not, thanks, Philip, for a really stimulating talk and questions and discussion.
Yeah, and if you're interested, just feel free to get in touch with me. My email is there on the slide still. Yeah, thanks very much for the invite.
Thank you.